So welcome everybody. I am going to talk a little bit about Bootable, a project that I help out with and I'm very excited about because it ties into a lot of work that I've been doing for years in the container space. Before we get started with the actual demo, I really want to talk a little bit about why Bootable came from and why I'm excited about it. Or not. There we go. And part of that goes down a trip down memory lane, my memory in particular, the evolution of operating system installs, because I was around for all of this, and I know a few of you were as well. Back when I got started with Linux in 1995, the way that you installed things was to compile everything, including the kernel. You had to compile the Linux kernel, and then you had to compile all the software to go on top of it. Anybody else remember Slackware? Oh yeah, we got a whole Slackware cloud here. Awesome. Yeah, so compile everything, which offered you certain options, but oh my God, it took a long time. Right? Installing a new Linux system was a 3-day weekend affair. And so it didn't take very long before somebody decided that they needed to solve that, and we got software packages, RPM being the first sort of major successful format, followed by Deb and other things. And then we started installing everything using these software packages. Installing those packages started to look hard when we got up to installing dozens or hundreds of systems. And so we added configuration management to handle installing the packages for us and automating it. But that still didn't solve some problems that we had with building systems, right? One was this config management and software package thing got really slow on really large numbers of machines. And since we're getting into cloud and the Amazon era at that point, we were dealing with large numbers of machines. Often they had non-determinative outcomes, and installing packages would fail and required manual intervention to fix them. One of the reasons everything was very slow is nothing was in parallel, and as a personal issue that bugs the heck out of me was the total lack of rollbacks, right? So installation would fail and you just had to take that system out of circulation. So starting in the cloud era, when we got over into VMs and public cloud, we started looking at instead, let's actually install images, right? So you build a virtual machine image with all of the software that you want, and then you deploy that image multiple times in the cloud. And that was definitely a big step forward, but it still had some problems. First of all, those tools for building those VM images were not user-friendly and were themselves annoying to automate and had to go through several generations. The images were extremely slow to build. This worked very well in the cloud, but on bare metal required setting up a whole ton of infrastructure, namely OpenStack. And we still didn't have rollbacks. So, still work to do. Now, one of the things that happened in the same timeline here was we got application containers, right? Docker came out, was officially announced in 2014, and the application containers had a number of really nice features, right? First, they were easy and simple to build. You could teach somebody how to build an application container in about half an hour. They built pretty fast. You had smaller images you could distribute easily. You could come up with schemes you could use them to deploy applications both on bare metal and in the public cloud. And for individual applications, they gave you rollbacks, right? New image didn't work, roll back to the old image. We wanted these features for doing the actual OS deployment. And that's where Bootable comes in. The idea of Bootable is to take all of those same great qualities that we have in application containers and use those to deploy entire systems. So to deploy those systems container images, to manage status and updates, and importantly, right, to support rollback. The way that this works is a normal application container, a normal OCI style application container, right, has only user space in it, right? It has apps, it has libraries in the base image. It does not have kernel space in there. In order to make the image bootable, we're going to need to inject kernel space into the image. So a bootc image is going to have kernel and POSIX space and everything else so that it can be booted as a complete system. That's going to make it somewhat larger, but fortunately, still relatively easy to do. So with that introduction, I'm going to go through a little demo. So here's how the demo is going to work. So first part of the demo, I'm going to show you when to take a container file. We use that container file to build a bootable container image with Kubernetes 1.3.3 on it, convert that to a disk image, and deploy it to a virtual host. What we're simulating here is something I do all the time, which is to deploy a system running a Kubernetes node, right? Because we want to have atomic deploy of Kubernetes itself before we have atomic deploy of applications running on top of Kubernetes. So I'm going to show you the initial host build in this first demo. Now, let me switch over to the mic here so I can actually do this. Now, I apologize. This is actually a video demo. The demo, actually doing the build itself and stuff, requires a fair amount of download bandwidth, which is never a good idea at a conference. Plus, a couple of the build steps are a little bit slow. So I'd rather show you the video. So the first thing is we're seeing here Podman Desktop. Why are we seeing Podman Desktop? Well, Podman Desktop is a great tool for building container images. And what we are doing here is we are building a container image. So the first thing that we're going to need to do is to go ahead and go, option a container file, bring that in. And this is our container file here. It looks a lot like other container files that you've dealt with. We have to do a few special things, though. One is we're going to need to base it off a pre-built bootc image, or you need to build that one yourself. And that pre-built bootc image, like I said, has the actual kernel in it rather than being just user space. The second thing that we do here, and this is actually strictly for the sake of Podman and Podman Desktop, is to tell it that it's dealing with a bootc image by adding the bootc label onto it. If you're using some other system, that might be optional. And then we're actually going to put a whole bunch of other stuff in it, and this has to do with the purpose that we're building the image for. So we're adding the repositories for all of the Kubernetes stuff from the official Kubernetes packages, and then installing a whole bunch of software, and then we have all of these init files. Because again, we're making this bootable, and the purpose of this is to make it a live Kubernetes node, in this case actually a node that can be a control plane node. And so we have systemd init files, some deployments, and init scripts, so that it will automatically boot up running the Kubernetes components. Now go ahead and name this and set it up to actually be deployed to my share on the Quay.io repository, and Kubernetes 1.3.3, and then we're going to go ahead and build it, and obviously you can do this all in the command line involving Podman, but I happen to like Podman Desktop. That makes something simple for us. I'm going to jump ahead a little here because it's not all that exciting to watch a container being built. So but it's doing all the usual things. We're still playing, yeah. And the container is now built, container image is now built, and we have it in our list of images. Now we want to do something with it, right? And because this is a demo, what I want to do is I actually want to add a wrapper to this image so that I can boot it in VM, actually in KVM. And so for this, I use the bootc extension to Podman Desktop and use the feature there that allows me to take this container image and build it as a disk image. So building this disk image, bootc gives you a whole variety of different kinds of disk images you can build for the different kinds of VMs. Right, we're going to build a QCOW because we want to boot it in KVM. But you can also build an ISO, you can build an Amazon AMI, you can take this container and build whatever other VMs you need for where you're going to deploy, or like I said, an ISO if you're going to boot it on hardware. Now, one of the things, and let me pause this, one of the other things, so we're getting ahead, that you also want to add in here is the toml config file, which at a minimum you want to use. This is a common thing in virtualization, right? At minimum you want to have in there who your user is, or you're not going to be able to log in or send commands over SSH to the built system, right? You can actually have a lot more in here than just this, but this is the sort of minimum. And in here I'm creating this core user that I can log into that then has sudo ability. And then we're going to go, there's also a whole bunch more options, but we are going to go ahead and build. Yep. And now I'm really going to skip ahead. Because we have to reformat the file storage, this takes a little while. And I don't want to have you wait through it, and this is one of the reasons why we're using a video. Okay, let's skip ahead here. Okay. How far do we have to go ahead before it finishes? There we go. Okay. And then you eventually get a success. We've built our boot image. We don't have it running yet. At this point, it's just a file system. Now, in this case, because I'm running it on KVM on my local system for the demo, go ahead and do virt install. And then this will go ahead and install and boot the file system image. And this only takes a few moments. And then having booted it, go ahead and find out what its IP address is and go ahead and log into it. And verify that it's running Kubernetes. So we've got Kubernetes control plane components running on this as an automated boot. And so you're like, okay, that's great, Josh. You just showed me a really complicated way to build a VM image. What's the advantage here? And the real advantage comes when it's time to maintain that VM image. Because the container workflow gives us a whole bunch of options for ways to maintain images more sustainably, reliably, and with shipping less bits, just period. So I'm going to show you how that works in a second demo. Where we modify a container file, because basically, modify a container file, update Kubernetes, push that to a container registry, because we're using container registry just like we do for application containers. And so this is the first advantage, right? You have one container registry, and it can handle both your system images and your application images, instead of having two completely different deployment systems the way that you do now. And then use that to update the virtual host. And I'll also show you my favorite thing, right? The important, what do you think my favorite part of this is? Yes, exactly. We're going to roll it back. So let's go ahead and do that. Clear this out. Okay. One of the things you notice here is we are running Kubernetes 1.3.3, but 1.3.4 is out as of a couple weeks ago. So how about if we upgrade this to 1.3.4? So what we're going to do is we're going to actually tell it, okay, we're going to use the 1.3.4 packages repository for building our container image, and we're going to build a new container image, here making sure that your naming is consistent for the repository and stuff becomes really important, so that bootc picks it up as an update. So do use consistent naming practices, and then we're going to go ahead and build this, like we did with the previous version. So let's jump ahead a little bit. Because this will take a minute. Okay, and we have built the image. And let's go ahead and push it to my repository in Quay. Very little needs to be pushed because most of the image has in common with the previous image, with the 1.3.3 image that's already there. So it really only has to push a few layers. And that's the advantage. You'll see that the images are rather large compared to regular application container images because of that whole kernel space. But you only tend to ship that kernel space once or occasionally when there's a major kernel update. And we should be uploaded. There we go. And so now it is time to go ahead and update. Now, there's two different bootc update paths. One is the way that you would put in patches, and that is bootc update, and that looks for a new version of a container with the same name. And this is going to tell me that there aren't any updates to 1.3.3, right? But I actually want to upgrade to 1.3.4, and I like to use switch to do that because there's extra upgrade steps. And switch says, and here, we're actually downloading, but what switch does is it says, this OS is based on this container image, but I want you to rebase on this other container image. Now, you can actually use that to rebase on any container image if you think the system will survive the swap out, because it's just shipping bits. But in this case, I'm using it just to upgrade to Kubernetes 1.3.4, and otherwise it's the same. And as a result, since it's only replacing the Kubernetes layer, or layers, it doesn't actually have to ship a lot. And for images that are being built by the bootc project and by the Fedora project, et cetera, we even had an intern work on layer optimization using some machine learning analysis in order to minimize the amount of layers being shipped for routine OS updates by predicting which layers would need to be updated at the same time based on history. So we have gone ahead and we have switched to 1.3.4, and that is our staged image, right? But we still have a booting image, and this goes through a swapping process, just like if anybody remembers CoreOS. CoreOS goes through a swapping process. The underlying mechanism is different, but it goes through a swapping process. You can bypass the swapping process, but in this case, because we need all of the Kubernetes services to restart, we do not want to bypass it, which means we want to restart the image. And, and that'll restart in just a second. And then we will go ahead and log back in and take a look at what's going on. There you go. Okay, and I'm going to go ahead and log back in. Kubernetes back up and running on this node. Check the version. So now you notice here that we now have 134 in the client tools, but we have 133 in the server. Why? Well, because we haven't upgraded Kubernetes itself, right? Kubernetes needs to upgrade. All of the binary stuff for 134 is there, but we have to tell Kubernetes to check all of its metadata and everything, upgrade all of that, and then switch which version of the binary it's using. And of course, one of the ways that we would do that is by using kubadmin upgrade. Now, in this case, I'm just asking it for the upgrade plan so that we can see what it would be doing for the upgrade. And it goes through all the kubadmin checks. But here, it actually gives me a clean bill of health, right? It says, okay, we're going to go ahead and upgrade this. We're going to switch all of these control plane elements and everything else, and we can go ahead and apply. Imagine, though, it had found a whole bunch of problems. And it looked like I was going to actually have to take a bunch of extra steps in order to upgrade to Kubernetes 134. Well, then I might not actually want to have it running Kubernetes 134 in the system, lest somebody accidentally upgrade and break everything. Which means what we want to do is rollback. Ta-da. And we're staged for rollback, and then we just restart the system again. Okay, log back in, check that Kubernetes is running, and check the version. And we're back to being 133 all. So that's the basics of bootc in a nutshell. By the way, if you want to try that out, this demo was designed by one of my coworkers, Praveen, who's a bootc contributor, and so you can actually get it there. And try it out yourself, because it's a fun little way to learn bootc. So our advantages for bootc is there's no need to choose individual components to install on new systems or virtual systems. We can update stuff efficiently through image layering. You don't have any chance of a partial update, and you can roll back if update fails. As a matter of fact, one of the things I didn't show you is if the update failed to the point where the new system wouldn't boot, bootc will automatically roll it back so that you don't end up losing the system and needing manual intervention. All that happens, the update just doesn't happen. So what I'm asking you for here is please try out bootc. Please get involved with the project. Easiest way to try it out is go ahead and download Podman Desktop and install the bootc extension. Podman Desktop runs on Linux laptops like mine, but also Windows and Mac laptops. And you can play around with creating your own bootable images. And then join our community. Off the website, we have chat on Slack and Matrix, and we are very interested in contributions, including well-written bug reports, including testing on various platforms. bootc does support cross-compile, so please actually try out cross-compiling stuff and installing on weird hardware and telling us how you did. So thanks very much, and I hope you give bootc a try, and that is it for my time slot. Thanks.